Well, thank you so much for having me tonight. It's already been so much fun. It's really nice to be up here and feel like I've met some of you as opposed to just getting up here and talking into a sea of unknown faces. So yeah, thanks for hanging out with me this evening and letting me crash your party a little bit. So I'm really excited to be here. So I just want to talk to you a little bit about kind of my take on what it means to be a geoscientist in human exploration and what that means. So I am a member of the 2017 Astronaut Class. This is us. We are affectionately known as the Turtles, which you can see on my patch on my shoulder there. Has a turtle there. The class ahead of us gives the name to the next class coming in. So we were affectionately named by our brothers and sisters in the 2013 class. But I've had the pleasure of working with these 13 other people, 12 other people for the last 2 years doing training. And it has been a real joy. They're great people, but one of the real joys about it is that we have such different backgrounds. And I think it's worth noting how many different backgrounds we really represent. So we have test pilots of a couple of kinds. We have a submariner, we have an aerospace engineer, we have a couple of medical doctors, Navy SEAL in there, microbiologist, ocean engineer, and then there's me on the right, planetary geologist. So I think it really says something about where NASA is at and where NASA is going, that they selected such a diverse class and found it important that we have such a diverse skill set as we start heading into the next few years here. So let's talk a little bit about how I got the pleasure of being part of this group and how I got here. So I started out as a mechanical engineer when I came into undergraduate at Stanford. I knew from a pretty early age that I was interested in space and interested in the idea of being an astronaut. Never thought it would happen, but so I knew that I kind of wanted to follow down that pathway. And I kind of thought that engineering was the only way to do that. I hadn't fully done my research at the time, but that's what the easiest path in my head. So I came to Stanford and started studying mechanical engineering. And about halfway through my second year, I realized that mechanical engineering just wasn't for me. I didn't enjoy it, wasn't really that good at it. It just wasn't the right fit for me. And so I kind of I came to a crossroad, or what felt like a crossroads at the time, where I felt like I had to choose between this dream that I've had for a long time or choosing to do something that I was passionate about and really enjoyed. And it turns out that I didn't have to choose, luckily. But I think that there is something in that's important to take away, and that two things. One, kind of being brave enough to choose the thing that is interesting to you and trusting that will put you in a place that is fulfilling and worthwhile in the end, and not feeling confined to what it is that you feel like you should do. I think that's important to take away, and to not really give no as an answer, take no as an answer when you're pursuing your dreams. So anyway, long story short, I found geology. I basically opened up my course bulletin and started flipping through the pages and saw class titles like What Makes a Habitable Planet and Planetary Materials, and I was like, that sounds cool, what is that? And then I looked up and saw it was geology. That's when I found out that planetary geology is a thing that you can study. And I remember my first geology class. I'll never forget it. We learned about planetary accretion. So for those of you that aren't familiar, essentially the way that planets form from their infancy is you basically start with one grain in the solar system, one grain just hanging out. And that grain, just by chance, makes contact with another grain. Now you have a bigger thing that it has a little bit bigger gravity, which means that it is a little bit more likely to collide with something else. So it collides with something else. Now it starts to have more gravity, starts to get bigger, and so it starts to collect more things. And eventually, that happens for long enough to create a planet. And I remember sitting in my chair learning that day, and I was like, I'm definitely going to be a geologist the rest of my life. This is the coolest thing ever. And that kind of passion for it has really never gone away. So fast forward, finished my degree in geology, left mechanical engineering behind, and then I went on to study the geology of Mars in my graduate work. This is a landslide in Valles Marineris on Mars, just one of the landslides that I looked at, but I was particularly interested in understanding why these landslides have such long runouts. So they run out further on the surface than physics says that they should, which suggests that there's some extra mechanism that's happening that's causing this run out. And it was a particularly interesting question, thinking about whether the role of water on Mars and maybe whether that was involved in forming these features. So the short answer is what we found was that these landslides were forming into, being in place into clay layers, or kind of, so if you can imagine slipping in the mud, kind of the mud layer beneath these, clay layer beneath these landslides was allowing these landslides to have longer runouts. It's kind of the short takeaway there from my thesis. Really enjoyed doing that and using Earth as an analog for that as well. For the students in the room, I just want to take a second and make a plug for internships, particularly NASA internships, but any internships will do. I was able to, I had the opportunity to have intern a few times at NASA, both at NASA Ames while I was an undergraduate, and then also at the Jet Propulsion Laboratory while I was a graduate student in LA. And those internships really were what solidified for me what it meant to be a planetary geologist, what those possibilities were, what that career would really look like. When you're sitting in a classroom, you can, find a subject interesting, but it kind of can be a different ballgame sometimes to really see what that looks like in a practical sense. So for me, internships really cemented the career path that I wanted to pursue. So I would encourage you guys to do the same. The summer 2020 application deadline for NASA internships is March 8th, so you have a little time to get on it. And the picture back here is of a Mars analog that I was able to be a part of through one of my internships. This is out in the Utah desert, and we did an analog Mars mission. So just as an example of the kinds of things that you can find yourself getting into. So following my following my graduate school, I pursued a postdoc at Caltech. And Caltech, of course, is very close by to the Jet Propulsion Laboratory, where the Mars Science Laboratory mission is run out of. So I was able to be a member of the science team on that mission, which was really just so much fun. I really enjoyed the aspect of, there were kind of two aspects to it. There's the operations side of kind of driving the rover, if you will, and then the kind of scientific research side of it. So it was really cool to be able to do both of those things, and be able to kind of wake up in the morning and see, the new images that have come down from Mars that only 3 other people have seen. If you're on the West Coast, see it first. And to be able to look at those and make decisions about where you want to send the rover next, you and 500 of your best friends, is just a really awesome experience. And it was a really important one for me. I really learned, I think, in that role, the importance of being able to work together as a team when you have different skill sets or you have different things that you bring to the table. So working with scientists and engineers in a new way for me was really enlightening and really powerful. And that's something that I carry with me.
That's a self-portrait, right?
That is a self-portrait, correct.
Yeah.
Yep.
Ask you is how did that happen?
Long boom.
The geologic feature?
No, how did
Yes, that's an engineering marvel that I don't understand at all. But yes, there's a whole series of movements that the arm is able to take a selfie of itself and then remove its arm from the photo. Yeah, way better selfies than me. So following my postdoc, I saw that NASA was accepting applications for the astronaut role, and I figured I would put my name in the hat, figuring that I would just be a good experience for me. But yeah, it worked out. So the selection process is actually it's very straightforward. It starts out with just submitting your application, just submitting a resume even, through usajobs.gov, just like you would apply for any other federal position. And it just goes off into the ether, you don't hear anything for 9 months. It's great. And following that, eventually you start hearing back and kind of check your references, and then they bring in the first group of people. It's somewhere around 500, I think, the first group. They bring, not all at the same time, they bring you in separate weeks for a few days at a time and just start to get to know you. Do lots of medical testing, a little bit of psychological testing, but mostly just kind of put you in groups and see how well you work together as a team. Turns out that that's a really, really big part of what we do. So there's a second round kind of that, and then they make the selections. So the big question that we often get is, what are they looking for? And unfortunately, I have no idea. But I'll tell you what I do know. So there are basic requirements, which are listed on the website, but having a bachelor's and a master's this time, and 2 years of experience in a STEM field, science, technology, engineering, mathematics, so you guys are all good. And then there are some medical requirements as well. So there's some anthropomorphic measurements, eyesight, general health, those kinds of things. Then kind of the sugar on top, the operational experience seems to help. Ability to work in a team helps a lot. But ultimately, it's going to be your attitude over your experience. Somebody told me once that they are looking for, especially the astronauts who sit on the board, are looking for somebody that they would be willing to live in a tin can with for an extended period of time, because that's legitimately what's happening there. So that's the only secret that I can come up with. But I will say, just to tie it back to kind of my pathway to getting here, I do think there is not, I'm positive there's not one path to becoming an astronaut. You saw in my class how many different paths we all took to get here. So it's really crucial that you just find what it is that you love and pursue that relentlessly. Be the best at that you can be, and that's the best way to set yourself up for success, no matter what you end up doing. Great, so I will just go through some of the training that we did pretty quickly. I do want to leave plenty of time for questions. So our training had kind of 6 major components, if you will, and I'll go through each one of them. The first was International Space Station Systems. So we'll go into a little bit more detail on the ISS a little bit later if we have time. But this was a really important part of our training. We essentially learned how to live and work on this space station and how to stay alive in space without the help of anybody aside from your crewmates. So this kind of trainer here that you're looking at, this is a relatively high fidelity mock-up of the International Space Station that we have in a large warehouse over at Johnson Space Center down the road. And so this is where we do a lot of our training. It's interesting, I've heard from crew members who come back that it can be kind of disorienting once you get up there because you spend so much time in Building 9, is what we call this. You spend so much time standing here like my classmates are, but when you get up in space, you don't know, your body doesn't automatically know which way is down. So you're using all three dimensions, the whole volume of that space in a way that we are not able to train to do. So it can actually be really disorienting when you get up there. It's interesting. We also train in robotics. So we have a large robotic arm outside of the space station that we use to grapple to our cargo vehicles, our resupply vehicles. This is a large partnership that we have with the Canadian Space Agency. So over here on the right is one of my classmates, Jenny Gibbons. She is one of our Canadian classmates. And speaking of international collaboration, another part of our training is Russian language. So this is one that some people would say is the hardest part. It definitely flexes your brain in a different way than the other pieces of it. But it is really important, especially now. You can see this is the most recent crew to have gone up. This is Jessica Meir on the right is the US astronaut. And they are in front of, that's a Soyuz at the top, that's in front of their vehicle, their Russian vehicle that they took to get to the space station. That's currently our only ride. We'll talk about some other options in a second, but our partnership with the Russians is really important for getting there and then once we're up there as well. Another big part of our training is EVA, so extravehicular activity or spacewalking. So we have a giant pool close to the Johnson Space Center down in Clear Lake. It's 40 feet deep and wide enough to fit almost the length of the International Space Station. At the ends, we kind of have to curl it around the corner. But we have giant mock-ups of the outside of the space station. So you saw the mock-ups where we have the inside mocked up. Here in the pool, we have the outside mocked up. So these two are on the US lab portion, and you can see the truss, the long segment of the ISS in the background. So we dive essentially in these pools, in this pool, in these suits. So we learn to get comfortable in these large suits. It kind of feels like you're learning to use your arms and legs again. It kind of is really a new phenomenon, but it's really rewarding as much as it is challenging. We also, as mentioned, we also learn how to fly jets. So this is the T-38 that we have at Ellington Field, also nearby Johnson Space Center. And we use these jets largely to help work on what we call SFRM. So I don't remember what the R stands for, but this is classic NASA. But the communication amongst your crew. So learning and practicing how to communicate with each other. And for the T-38 especially, it's useful training for us because there is real operational risk involved. You know, we do a lot of other things where we simulate that kind of risk or simulate that kind of scenario, but this is one of our few platforms where there is real risk involved and the decision-making piece of it is actually real. So that helps us kind of gauge some of our communication and decision making around that type of scenario, which is obviously important for CISO. Then the last component is one I kind of mentioned the importance of, this expeditionary and team skills portion of our training. So this is us at land survival training, building a tent. And we also participated in NOLS, National Outdoor Leadership School in Canyonlands, where we worked on our leadership and team skills as well. These really are the just really important skills to have when you're living in confined spaces with just a few other people. But my favorite part of training, of course, was our 4 weeks of geology training. So we had 2 weeks in the classroom and 2 weeks in the field in two separate locations. So in the classroom, we had a team of expert instructors come and help us and learn all of the basic foundations of geologic principles that we'll need to know. We also, in the top right there, we're also able to stop in the lunar lab at Johnson Space Center and check out some moon rocks, which was really, really awesome as well. Then once we were done in the classroom, we went out to the field. Here we applied what we learned in the classroom, and we really were able to use these sites that we went to. So we went to the northern Rio Grande in New Mexico, and the Flagstaff area in Arizona. And we really used them as analogs, mostly for a moon scenario, lunar analogs, looking at a lot of volcanic rocks. So we were able to use tools, so we can see some sampling that's going on in the bottom left. We use XRF, getting used to using instruments and tools in the field. We even had some sampling constraints put on us where we had a limited number of bags, a limited amount of weight that we could bring back, just to get us to start thinking along those kind of operational guidelines while we're trying to maximize our scientific mission. And then presented our maps and cross sections at the end of the week. One of the really cool aspects of this training was being able to be a part of the legacy of the Apollo astronauts. So this is Jim Irwin and Dave Scott, Apollo 15, working about 10 minutes from where we were doing our training, which is by design, of course, in the Flagstaff area. So it's just really neat to be able to kind of stand on the shoulders of those giants and really walk in their footsteps. I just wanted one anecdote that this room will appreciate, I think. So these guys, the Apollo astronauts, had the equivalent of a master's degree of training in geology before they went for the Apollo J missions. So they had a lot of training in the field. And while we were at Flagstaff, our class was able to meet with Charlie Duke. He happened to be at Flagstaff as well. And we were chatting with him, and he knew we were in town for geology training, and so we were asking, what was the most impactful thing about geology training, or what do you have any, advice or words of wisdom about that? And he, was like, yeah, it was really great, we really enjoyed it. It's like, but once you get up there, like, if you, whenever in doubt, just bring one of every color. I was like. So my classmates will never let me forget that. So we talked a bit about training. So now the big question is, where will we go and how will we get there? And I'm not sure I'll be able to answer that by the end of the evening, but I'll give you the options at least. So the kind of main destination right now is the International Space Station. It's a U.S. national laboratory, 250 miles up. We actually have been on the ISS, meaning that we have had a continuous human presence in space for 20 years this year, which is pretty outstanding. What have we been doing up there? It turns out the answer is actually quite a bit of geoscience. So we have 126 Earth and space science experiments and 2 dedicated facilities. One that is an automated system to acquire images of the Earth, and then one that is a facility for remote sensing payloads that you can put through the window. And on top of that, you also have human beings, which function basically as a third facility in that with just a still camera out the windows at the bottom of the space station, it functions as a really excellent instrument as well. You can see here this image of this, I think it's the Rhinoke volcano, I believe. That erupted in June of this past year. It was totally dormant, hadn't erupted in thousands of years. Nobody ever expected it to. It's an uninhabited island. But the crew member, the ISS crew member, saw indications of this happening and actually emailed one of our geology instructors and said, "Hey, Jake, I think this volcano might be about to blow." And he kind of was like, "Well, that's I'm really glad you're interested, thanks for emailing, but it's been thousands of years, right?" And then this happened and she got this shot. So it just speaks to the unique perspective that we actually get in terms of Earth observations from the ISS and the capabilities that enables in terms of monitoring and surveying disaster response. Let's see. I mentioned that the way that we get to the ISS right now is the Soyuz, but coming up, hopefully this year, is the commercial crew program. So we have the Boeing CST-100, the Starliner, and the SpaceX Dragon, which should be launching this year. And that will be the first time since the shuttle that we will be launching from U.S. soil, and launching from Kennedy Space Center, Cape Canaveral. So it'll be very exciting when those come on board. The other possibilities for destinations, of course, are the Moon and Mars. So our administrator, from direction from the president, has said that we are going to the Moon to stay. And that it will be a stepping stone towards Mars. And shortly after this quote, I think, is when he announced that we would be doing that boots on the ground in 2024. So that is the goal. I won't go into this chart in very much detail, but I'll just point out that the kind of idea behind the Artemis program is that we will send these commercial lunar payload services, so the CLIPS, and that will deliver these science and technology payloads. So this will kind of set the stage for humans and provide some of those resources on the surface that we'll need when we arrive. So that will be happening very soon. Those are in the kind of bidding stages right now. Then we will have the Artemis missions here that kind of follow, and Artemis 3 here being the 2024 mission with humans on the ground. All right, quickly, I just want to talk about the landing site that has been proposed for humans. So we are interested in the South Pole. And the reason for that is because of the resources that are available there so, that would enable us to stay for a long time. So it is a very different mission profile than for Apollo, where we aren't going for the same reasons or with the same goal, and so we're going to a different place. So great. So we are going to a place called, or the plan is to go to a place called Shackleton Crater that is at the south pole of the moon. And the reason for that is if you follow these shadows going around, so Shackleton is right in the center. That's Shackleton. So if you follow the shadows around, you can see that most of the crater, the inside of the circle there, is shadowed all the way around. So, and it's also worth noting that nearby, kind of around the rim, that a lot of that stays pretty light. So the juxtaposition of this blue, what's being colored in blue here, is a permanently shadowed region, and that is next to what are consistently illuminated regions. So that is ideal for both from an operations perspective, in that we, the advantage of the permanently shadowed regions is that they might be a source of volatiles on the moon. And so those could be used as resources, both as crew consumables, as well as, crew consumables, so oxygen and water, as well as fuel in the form of methane. So that's really of high interest to us, but the illuminated areas are important as well, so we can maneuver and get in and out of this area.
Mean solar panels.
Sorry?
Set up solar panels.
Yes, exactly. So in the center here is Shackleton. So this is a shaded relief map here, so you can see that it gets pretty deep there. So Shackleton is actually 3 times the depth of the Grand Canyon, and about 18 times the diameter of Meteor Crater, which is what this is up here on the right. So we spent a day in Meteor Crater as an analog, and after doing that for a day, Shackleton is going to be a lot. There's definitely still significant challenges that need to be overcome with this landing site, but the rewards will be worth it. We also have challenges to overcome in terms of our suits as well as our tools. So this is poor Jack Schmidt, who is just trying to put a sample in a sample bag and having a hard time. So we definitely are working on the next generation spacesuit as well as next generation tools to just make us more efficient on the surface. So after we successfully complete a successful mission on the moon, then we'll head to Mars. That's all I have to say about that. So I just want to leave time for questions, but thank you so much for having me, and most importantly, congratulations to all the scholarship recipients.
Be setting solar panels up there with sunshine.
Yes, so that's it, yes. So you would set up kind of your actual base, living space along the rim, and then you could access the crater. But the idea of accessing the crater is not as simple as it sounds, given the topography that I just mentioned. So there is more work to be done.
What kind of volatiles do you expect you're going to find in Shackleton?
Largely water ice. Sorry, I didn't make that clear. Yep.
Did you see water ice there from the sensor?
Yes, so there are several different databases that all kind of converge on water ice. I think there's some neutron data. There's also just looking at it visually, there's brighter reflectance in the crater inside it. So there are a few different lines of reasoning that would have us suggest that, but it is definitely not. It's definitely not a certainty. So that's about.
My turn. You mentioned that the class of 2013 named you guys the Terminals. Are you allowed to tell us what the next class may be named?
That depends entirely on who they are. Yeah, it usually will kind of come up in training or something that happens. We got named the Turtles because during our announcement, the Vice President came to Johnson Space Center and introduced us and gave a speech, and he mentioned that we are like turtles on a fence post. And in that, we didn't get there by ourselves. So it was a nod to our support systems and our families and friends that helped get us there.
Out of everything that I'm pretty sure you were wanting to see and looking forward to, what is the one thing that you are excited the most once you reach above our skies?
So one thing that I have heard has a pretty profound impact on people is getting enough above our atmosphere and above our surface that the perspective of looking down on the Earth, one gives you a really good sense of how small it is and how fragile our ecosystem is, how small, how thin our atmosphere is, and how insignificant seeming our Earth is in comparison to the vastness of space. And kind of on a related thought, that you also are not able to see boundaries from space. And we have our boundaries, create all kinds of division and all kinds of stress in our world, but from space you can't even distinguish one country from the next, one culture from the next.
Can you comment on the efforts to explore for helium?
Probably not intelligently. Yes, I know that there are several different resources that are worth exploring for, but I think ultimately there's a prioritization, right? If we're not confident that we can find more than one type of resource in the same location, we can only go to one place, and within reason, even if we end up with a rover of some kind. So I think my opinion would be that we would want to get the most bang for our buck, right? So a water ice type of situation where we can get the human resources as well as the fuel, that seems like a worthwhile cause to me.
Okay, so what kind of tools, I'm here.
Thank you.
What kind of tools do you perhaps have available to you as a geologist in space, like lab techniques, or how much stuff would you have to send home to get tested in this?
Yeah, great question. So I guess the answer could be that it depends. I guess it depends on some of those payloads and systems that we send ahead of us, and maybe it's would be a good idea to send something, choosing to send something on the surface so that you wouldn't have to return it. But in terms of actual analytical capability, I think most of it would be, I guess my only paradigm for it really is the Hall missions, and most of that was kind of set and go and or bring back. There wasn't a lot, there also just wasn't as much time for iteration, right? So there wasn't the capability to, pick a sample, analyze it, and then make a decision about where else to go. That just wasn't the style of their missions. So it's an interesting question, and it kind of goes into part of the question of what do surface operations look like on the moon? And it's an outstanding question right now. There's a lot of different opinions about what that actually looks like. You know, do we have really set EVAs? Do we go out the door and know exactly what the mission is and not stray from that? You know, we are at the point now, different from Apollo, where we have pretty high fidelity data sets in terms of, you know, orbiters and soon to be rovers, that we can, you know, pretty easily narrow down where our points of interest are. So do we just lay those out, have the astronauts go, you know, hit those 4 things and don't touch anything else? Or do we kind of give astronauts the freedom to go out and, you know, here are our top priority kind of regions, but we trust you to kind of make your choices about what you think is interesting and, you know, where do you want to apply more analysis. And I'm not sure there's an answer to that question necessarily. It's kind of two camps of how you get things done, but it's definitely an ongoing question right now.
How do you
So,
decide the sample
Right
size?
here. It's ready.
Yeah.
Hi. So if you were to pick a location on Mars to land, not from like a feasibility standpoint or anything like that, but just from a geologic point of interest, what would you choose and why?
You're gonna get me in trouble.
Sorry.
Jezero Crater.
We're sending one.
Right now, just kidding. Sorry, so Jezero Crater is where we are sending the next Mars rover, Mars 2020 rover. Can you guys hear me? Which I do think would be very interesting, but I would sense that we already have something there. So if it were totally up to me, I didn't have to cooperate with anybody else. It's $5 billion rover. Okay. I would probably send it to Valles Marineris. And partly because I obviously have vested interest there, but I also think, you know, canyons are nature's free pass, right? We get access to lots of layers, lots of history, all in one place, and I think that would be invaluable in terms of deducing the whole geologic history of Mars. And that reminds me that's an interesting piece of Shackleton Crater as well. You know, we talked about the operational benefits of going there. And challenges as well, but from a scientific perspective, craters are very similar in that they are nature's free excavation of material. So you're able to get down into the depths of geologic time all in one place. And the volatiles, the history of the volatiles themselves, and how that interacts with the geology of the crater would also be interesting as well. So we do get kind of lots of benefits of that type of site.
What's your favorite movie about space?
Probably The Martian.
How do you decide the sample size?
The sample size. So, good question. So ultimately, the overriding factor is the amount of mass that you're able to bring back. So the amount of mass that you're able to, like, literally lift off the surface with the amount of propulsion that you have, and land safely. And so all of the dynamics of that, space flight are going to spit out a number of kilograms of mass that you're able to bring back. We're fighting for that number right now. But then from that, once you're given that volume of material, I think honestly what determines sample size is what you can carry, what you can literally physically move from its in situ spot to back to the lander. Either physically, individually, or if you have some, wagon or tool or something. And then the second one would be storage of some kind. So the size of your sample bag, or the size of, figure out how to freeze the sample, the size of the container that's able to do that. I think you'd be limited by like those linguistics.
But what if you've got the rainbow of colors and you've got to get them all back to Earth?
Yeah, I mean, that's the exercise, right? I mean, that's the interesting question, is you're going to have to prioritize. And that's what the Apollo astronauts did too. And now we know their strategy for doing so, but they had to choose which rocks they thought would tell us the most about the origin of the moon and the Earth, and had to do so with limited analytical capability.
So you said that the plan is to go to the moon and stay at the moon. How long? Is there a rotational plan for how long people are expected to stay?
That's a good question. I'm actually not sure that I've heard an end number for that. That chart that I showed of the Artemis program, there's a like part 2 of that shows up through Artemis 7 or 8, I think. So I think at some point there was some kind of funding for that. So yeah, actually that probably is the answer right now. It would, as long as the funding exists for it, quite honestly. But the idea would be that it would be a jumping off point to go to Mars. So if ever those had to come in conflict, I think I guess that would be a decision to be made then, but I would think that it would be, that we would give up the presence on the moon in order to pursue Mars. But there are lots of, there's a huge, large political aspect to that I can't answer, though I wish I could.
Hi, yeah. I just had a question. So you graduated with these peers from all different backgrounds, and how does that play into the role that you guys play on like the ISS or going to Mars? Like, do they weight geoscience, like going to Mars or going to the moon?
Yeah, so for ISS, right now, our backgrounds, we all become generalists. So we all come into the program, we all go through the same training. So everybody on the list with all their different backgrounds, we all did the exact same thing. Yeah, the pilots had a little bit less flight training than we had. but everything else, we all kind of did the same thing. The idea is that on ISS, we all are able to do all of the tasks. We're all able to do the science and do the maintenance and keep ourselves alive and productive on station. But for Moon and Mars, it could be very different, right? And certainly in Apollo, people had specific roles and things they were filling. So I don't know. Yeah, I'll keep you posted. But, yeah, let's see.
Did you get to go to Star City? Hi.
Thank you.
Did you get to go to Star City in your Russian training? And I have a second question too, because that one's just really fast. Space junk in terms of satellites and things, is that something that actually concerns you and that you're aware of in your mission planning?
Yeah, so first question, I have not been to Star City yet. It just wasn't part of our training this time, but we will go down there if and when we get assigned, and we'll do training there. No matter what vehicle we end up taking, we'll definitely spend some time down there, and I look forward to it. For space junk, so it's something that we are aware of in that we know it's a thing that's going on, but it's something that's mostly taken care of, almost entirely taken care of from the ground. So there is a person or a console in mission control that is monitoring that. So we have eyes on that material, if you will, and we would really only be aware of it if it were becoming an issue. And there are ways of mitigating that. It really wouldn't, we can just maneuver station a little to the left, a little to the right. So it's never been an issue, but it's something that we prepare for as a possibility, but not something that I don't think the crew thinks about while out there.
Hi.
Thank you.
Yeah. Can you tell us a little bit about what your day-to-day life looks like and how that's changing with this graduation? Congratulations, by the way.
Nice. Yeah, absolutely. So we just finished training As I said, we're full-fledged astronauts now. But what that means is that we go back into the office and we are given a technical role of some kind. So you saw there's kind of a lot of moving pieces right now in human spaceflight, and so we are all we get dispersed to help with different roles. So one of us is working on the suit. One of us is working on the Orion capsule to take us to the moon, looking at displays and that kind of thing. I'm actually going to be helping with commercial crew, so helping with the logistics around launch and landing out of the Cape in Florida. So it looks a little bit different, but a lot of that actually, we do still have to kind of maintain currency. So we still fly a few times a month. We still have to go to Russian class tomorrow. A lot of it we still kind of do to maintain.
Yes, from a fully recovered former mechanical engineering student. Thinking about the etymology of geology, the greater study of Earth, including solid, fluid, and gaseous parts. Are we going to need new words for studying other planetary bodies and asteroids?
I think they already exist. I think they're just not widely used. But Mars is areology, is that right? Something like that. Because as in Aries, Mars. And I think if you looked it up, I think they exist for everything, but people just don't use them. But maybe they'll become more commonplace as the idea of studying geology on another body becomes more commonplace.
Dr. Jenkins, thank you so much. It's been a fantastic presentation, and I know we're not over yet. It's just my turn to ask a question. We've recently had one of your earlier classmates return from the ISS. One of the female astronauts made a trip of a total, was it 338 days?
Sounds right, yeah.
And she had slightly less than normal bone density loss and slightly less than normal organ function loss. And she was pretty well recovered and walking around after like 4 hours, which is amazing. So have you been involved with any of the evaluation out at NASA or Johnson Space Center or Brooks doing the physical durability study effects for arriving, staying on the moon, and then going on Mars and spending like a year and a half, 2.5 years out there under low to no gravity? That's a lot longer period than what we've done before. I'm just curious your experience and outlook on that. And thanks for a wonderful presentation.
Yeah, absolutely. It's a good question. So it is something that we are thinking a lot about, especially I mentioned that I was working on launch and landing around commercial crew. We're also thinking about Orion as well. So we are, in those programs, we're moving back to capsules, right? So capsules that are landing in the ocean as opposed to the Soyuz lands on the ground. And with the different mission durations, the different amounts of exposure, and the idea of sitting in a capsule that is kind of buoying around in the ocean until the Navy can find you, it is really a big deal to think about what state those crew members will be in, and especially in a contingency scenario. Building our requirements and our capsules around the capability of those crew members to self-egress or to get out of the capsule by themselves if they need to, or come down, climb a ladder, or even just get out of their chair if that's a requirement. If they're on their side, if the capsule ends up on its side, the probability that it can happen. Are they able to get out of their seat if they are what's called a deconditioned crew member? So there's a lot of work that goes into thinking about what that looks like, but it is a hard thing to test because it's a hard thing to replicate. It's how do you pretend to be a crew member who just came back from being on the moon for a month. it's hard to replicate that physically. And so to drive requirements around it is a tough problem, but a really important one.
We have to send rugby players.
Thank you so much for representing us humans in space. It's amazing. Is there any relation to the Shackleton, famous Earth explorer, to the crater Shackleton?
Yes, I meant to mention that. Thank you. Yes, so the Shackleton crater is named after Ernest Shackleton, I think is the first name, who was an Antarctic explorer who went out into the unknown in a similar way.
His grandson studied geology with me.
No
in
way.
Ireland. Yeah. Jonathan Shackleton.
Awesome.
It's amazing. I didn't know that.
Yeah.
Any more questions? We're winding down, everyone. We take just one or two more questions.
So as we start taking these larger steps into the unknown, do you see, is the decision-making done more on the ground or more on board? Has technology changed it, or is the nature of the riskiness or whatever?
Yeah, that's a great question. Definitely something that we're wrestling with right now. We have built all of our systems, all of our means of communication, all of our understanding of how we execute procedures. Our whole space business is dependent on a ground that is able to respond in a reasonable amount of time, aside from a real contingency scenario. And so when we talk about thinking, when we talk about being on the other side of the moon or being on Mars, and not being able to communicate with the ground in the same way, it starts to get back to that question about crew independence and how much are you willing to we won't have a choice, but it's not something that we are used to kind of let the crew be on their own for an extended period of time. So it's going to be a really big transition for the team. We work with a really large team of awesome engineers and scientists, and we really are just the tip of the iceberg. It's going to be a really big shift for everybody to start thinking about having an exploration mindset when it comes to ground communications.
Thanks.
This way. So kind of back to the field methods you might have out there. Are you seeing any kind of bias to what we would study if we were to land on Mars? Like, will we study more like geomorphology, sedimentology, volcanology of it, or is that something more based on where we can end up landing, I guess?
Good. Yeah, interesting. So I guess it depends on what the goal is. We have our rovers that are going to Mars, and the goal is to look for signs of or preserved ancient life. And so that goal drives a very specific type of geology. Right? We are looking at more sedimentology, geomorphology, because those are the types of environments that life would be preserved had it been. But sending humans, we probably would try to avoid any possible life. So maybe that would bring us to a very different place, and we probably would be driven by different things, looking for different resources or safety in a different way than we think about safety for rovers. So it'd be different.
Have you had a chance to realize after going through all your training that you're at the pinnacle of the space program and sort of been able to take that in, to understand that you made it and you're it?
I think what the 2 years of training has really helped me wrap my head around is that we really are kind of just that, the tip of the spear. And we are really just kind of a representation of a much bigger thing.
But you're going to be out there.
That's true, but it sounds trite when I say it, but we legitimately bring everybody with us. And we wouldn't be able to do it on our own. We down. It really is, just kind of seeing yourself as a representative and being lucky enough to have that honor.
One more question. Jessica, people don't want to go. You have just inspired everyone.
Thank you for your talk, first of all. Getting back to the team aspect of things, what was the one thing in your team training with NASA that maybe you weren't aware of that was important to team building, or something that you didn't expect from all your previous work that you think is the most important, or some of the most important aspects of team?
Sure. So the first thing that comes to mind, I might have a different answer if I took a little more time to think about it, but the first thing that comes to mind is because of our difference in backgrounds, our difference in leadership styles really comes out in those types of environments. And I think we all have biases towards which kind of leadership styles we like or expect or respect. And finding a way to learn to be able to have different types of leadership styles and apply them in the right scenario where that leadership style is needed in that moment with that group of people is something that I'm not sure that I really had the experience of doing. I think this type of scenario pushes your bounds, pushes your limits in really good ways. And for me, that's been one of them, is kind of, trying to understand when to follow, because there are definitely times that it's important to follow, especially in a spaceflight type of scenario, and when it's important to stay up with it.
Thank you. Come on over. We have a few minutes. So we have a special gift for Jessica, and Jeff is about to unpack it. Are you ready? Mars. Actually, what are you talking about?
Yeah, that's my news. Here it is.
Model based on orbital photography, I guess, is one of the pros. And it also has some texture, so it's the neatest Mars I've ever seen. That's 3D. We mounted it on a plaque like we normally do for our speakers awards, and we say, HGS Scholarship NIght 2020, Astronaut Jessica Watkins speaker, safe travels. Thank you, Jeff. Jessica, we have a special book for you about pioneering women, and it's got a very special inscription from a very special person in the audience. And you're a pioneer, and we wanted to say, we hope you enjoyed some stories. So, I hope that you've been uplifted and inspired, because I know that I have. And tonight's all about the scholarship awardees. We know you continue to do wonderful things, and we wish you great success ahead. And a special thank you, Jessica, for being with us tonight. Really appreciate it. And I'm taking a good look at your boots, because those are geoscientist boots, and I can't wait to see them walking around on a planetary body. And when you do, you're going to remind all of us, never stop exploring. But he's not here tonight, so we'll have to give it to him later. Voila! Thank you, everyone, for coming. If you want to